Hi, afternoon, everyone. Today we have a speaker, Dr. Shibata. He's from NUS, and he will talk about invariant subvarieties with a small dynamic degree. Please, if we have question, you can use the chat. We can check. Thank you. Yeah, please start.
Okay, thank you. Thank you so much. And I thank the organizers so much. I will talk about invariant subvarieties with small dynamical degree. This talk is based on a joint paper with Professors Matsuzawa, Men, Shibata, Jan, and John. It is uploaded in archive in the same title. Okay, first setting is K is a arbitrary field and X is a smooth projective variety over K, and F is a dominant morphism from X to itself. Then we can define the first dynamical degree of F by this formula. D1F is the limit of this intersection number powered by 1 over n. Here, H is an ample divisor of X, and we take the product of H by Fn, and take intersection with other ample, the same H. And then the limit converges, and it is independent of H. And this number is larger than or equal to 1. And D1F is a birational invariant of F. This means that if we take birational conjugate of F by any birational map, then D1 is preserved. And dynamical degrees can be defined for any dominant rational self-maps. Okay, this is dynamical degree is defined over any fields, but height functions are defined over some arithmetic field, such as number field. So we assume that K is a number field, but we consider arithmetic situation only to see our motivation of main results. So our main results are our main results hold over any algebraic closed field of characteristic 0, but I will introduce arithmetic setting for motivation. Okay, first I introduce height functions. A Cartier divisor D on X determines a logarithmic height function denoted by H sub D. This is a real valued field whose domain is the set of rational points on X. HD is determined only up to a bounded function. So there are many choices of HD, but HD is determined up to the difference of a bounded function. So especially the growth by iteration of a self-map can see independent of the choice of HD. So we can define the following arithmetic degree. The arithmetic degree of F at a point X is a rational point of X, is defined by this formula. This is here H sub H plus is simply the maximum of H sub H and 1. So this is just for the convergence of the limit, so not essential. Anyway, we define alpha x by the the ample height of fn of x powered by 1 over n, and taking the limit. And arithmetic degree converges always, and in this situation, and it is independent of the choice of ample divisor and the associated ample height function. And similar to dynamical degree, it is larger than or equal to 1 for any point x. And then a fundamental relationship between arithmetic degree and the dynamical degree is the following inequality proved by Kawaguchi, Superman, and Matsudawa. They proved that the arithmetic degree of any point at any point is always at the most the first dynamical degree for any point. And Kawaguchi and Silverman also conjectured that the equality holds if the F orbit is dense in Zariski topology. The orbit is the set of x, f of x, f2 of x, and so on. And first, we generalize this conjecture so we call the generalized conjecture by SAND conjecture. First, assume that the first dynamical degree is larger than 1. I explain about it. If the first dynamical degree is equal to 1, then all arithmetic degree is equal to 1 by this inequality. So this case is not, this case is trivial. So we assume this condition and take any positive number d, then the set dfd, df of d, defined by df of d is the set of rational points such that this point has extension degree at most d, and this point has a small arithmetic degree. Small means the arithmetic degree does not attain the first dynamical degree. We denote this set by ZF of D, and then we conjecture that this set is not Zariski dense for any small d. We can easily see that this conjecture implies the Kawaguchi-Silverman conjecture, because if we have a Zariski dense orbit with small arithmetic degree, then in any case, a given orbit is contained in any point of the given orbit has bounded extension degree. So we can bound the whole of points of OFX by some degree. So and any point of OFX has a small arithmetic degree because arithmetic degree is preserved by iteration of f. So the whole of x is contained in some ZF of d for sufficiently large d. And so this contradicts the non-density of Z of d if the SNND conjecture is true. So this conjecture implies the Kawauchi-Silverman conjecture. Okay, and we can the SNND conjecture can be made more precise. First, we define some notion. A closed subset G of X, G in X is a F-periodic subvariety with small dynamical degree, and we denote by F-periodic SDD subvariety for short. If first G is pre-periodic in this sense, and so we can define, we can restrict the dynamics to Fk of Z. So Fn can be restricted to Fk of Z, and we can consider the dynamical degree. Then this dynamical degree is strictly smaller than the dynamical degree of the ambient dynamical system. This is the definition. And then the SAND conjecture can be written by the following form. Assume D1F is larger than 1 and take any positive number D. Then the set ZFD is contained in the union of finitely many periodic STD subvarieties. Clearly, this form is stronger than the previous form, non-density, because F-periodic subvarieties are STD subvarieties are proper subvarieties, and so this statement implies the non-density of ZFD. But this form is, we can see that this form is equivalent to the previous one. So we are concerned with F-periodic STD subvarieties. So the first question is, how many F-periodic STD subvarieties does X have? For the SAND conjecture, maximum F-periodic STD subvarieties are important because we want to consider whether ZFD is contained in finitely many STD subvarieties or not. So we only we have to consider only maximal ones, and every pre-periodic STD subvarieties is mapped by some iteration of n f to an F-periodic STD subvariety. So pre-periodic ones are generated by periodic ones. So periodic ones are capital, important. So based on these observations, we consider the set SF. Let SF be the set of F-invariant SDD subvarieties, which are maximal among all F-periodic SDD subvarieties. And so S sub F2, S sub F3, and so on gives all F-periodic SDD subvarieties, maximal F-periodic SDD subvarieties. So we take the union of all S sub Fn. This set is the set of all F-periodic maximal SDD subvarieties. And then we can make the first question more precise. First, does S sub Fn finite set for every positive integer n? So And if so, how does the number of the cardinality of this set S sub Fn grows as n goes to infinity? Remark that these questions are valid for over any field. This question is based on arithmetic conjecture, the SAND conjecture, but these questions are purely algebraic geometric, so we can consider over any field. Okay, then we consider the simple case, easy case. The case we can compute the set SF directly. It is the polarized endomorphism case. X is a smooth projective variety, and F is a polarized endomorphism of degree Q. Q is larger than 1. This means F is a surjective morphism from X to itself, such that the pullback of ample divisor H is linearly equivalent to Q times H. H is an ample divisor. This is a polarized endomorphism. And then any F pre-periodic STD subvariety has dimension 0. We can see this by using H. So if we have an invariant subvariety of positive dimension, then the restriction of H gives the same polarization, the polarization of same degree Q. So positive invariant subvariety of positive dimension never have the same maximal dynamical degree. Small dynamical degree. So STD subvariety is always has dimension 0, and any F pre-periodic points are clearly STD subvarieties. So in particular, SF is just the set of fixed points in X. And so it is known that the set of S sub Fn is a finite set for any n, and the estimate of growth of S sub Fn is given by the Lefschetz formula. So we have this estimate. Based on this simple example, we conjecture the estimate of S sub Fn. Okay, this conjecture. In general case, in general dominant morphism on algebraic variety, the cardinality of Fn is bounded above by this term. Okay, we will consider this question and these questions for particular cases. Finally, in the introduction, I will explain the relation of the previous question to the SAND conjecture. For a variety, for a subvariety Y and the positive number D, Y sub D, Y of D denotes the set of closed points in Y, such that the extension degree is bounded from above by D. And then we assume 3 conditions. The first is the one of our main question. The set of if an invariant maximal SDD subvariety is finite. And we moreover assume two more conditions. For any F invariant subvariety y of x and for any positive number d, this set, the set of rational points whose degree is bounded by d and it is contained just in the inverse of y by f to s. This set is empty for sufficiently large s. And the third condition, for any positive number d, there exists a positive integer n such that the y has no rational points bounded whose extension degree is bounded by d for any f periodic STD subvarieties whose period is larger than n. We assume these conditions, then the converse of the previous implication holds. That is, then Kawaguchi-Silverman conjecture implies the SA and the conjecture. But we consider only the first one in this talk. This is purely geometric. Okay. Any questions? Okay. Okay, then we proceed. From now on, we work over an algebraically closed field of characteristic 0. And our first result is let X be an algebraic group and F is a dominant group homomorphism from X to self. And then first the finiteness holds. And the conjectured estimate also holds. We remark that this theorem holds even if F is the composition of a group homomorphism and a translation map. So in particular, the theorem holds for any dominant self-morphisms on semi-abelian varieties. Anyway, we only treat group homomorphism case here. And for simplicity, we consider the abelian variety case today. The general case is reduced to abelian variety case. So we assume X is an abelian variety and F is an surjective group homomorphism with D1F larger than 1. Sorry. And first, we prove this proposition. There exists a unique element of S sub F containing the origin, which is an abelian subvariety. We denote it by X of F. We see the sketch of proof. First, clearly the origin is F invariant because F is group homomorphism. And the zero-dimensional variety has small dynamic degree. So the origin is F invariant STD subvariety. So there is a maximal one. We denote it by Y. Y is an element of SF containing 0. And then let H be the abelian subvariety generated by Y. We consider this diagram. We take a sufficiently large number n, and Sn is defined by the difference of the first n coordinates, and minus the last n coordinates. And then for sufficiently large n, this this morphism is surjective. And so, and now y is F invariant. So, and the H is also F invariant. We can see because H is generated by Y and Y is F invariant. So this diagram is commutative. And then, sorry, it is D1 of F. D1 of F is larger than D1 of F restricted to Y because of the definition of Y. And now the power of self-map, taking the power of the self-map doesn't change the dynamical degree, so it is equal to d1 of fy powered by 2n, and because the above self-map dominates the below self-map, so the above one has larger than or equal to the below dynamical degree. So anyway, F restricted to H has also small dynamical degree, and H is now F invariant. So H is also an F invariant STD subvariety. So, but we assume Y is maximal. So Y is indeed equal to H. This means Y is an abelian subvariety. And similarly, we can show the uniqueness of Y. If we have another Y prime containing 0, then we define Z by the abelian subvariety generated by Y and Y prime. And this one also has small dynamical degree by considering a similar diagram. So by maximality, all are equal. So Y is unique. Okay. Now we can determine the set SF. SF is the set of X of F plus B, and B satisfies this condition. FB minus B is contained in XF. We can prove this. Yes, but I omit the detail. And then we take the quotient by X of F. The quotient map is pi. And then X of F is F invariant, so F induces endomorphism on X bar, denoted by F bar. And then because we contract XF, so S sub F bar is denoted by this formula. Yeah, S sub F bar is just the fixed point of F bar. This means so X of F bar is the origin, just the origin. And the correspondence from S sub F to S sub F bar is given by this map. So it is sufficient to compute the number of S sub F bar because the dynamical degree is also preserved here. So the fixed point of F bar is just the zero set, the zero set of this phi, F bar minus 1, F bar minus identity map. And so we set phi by this, and we set M by the dimension of X bar, then we can compute the cardinality of S sub F bar. It is degree of phi, and we can compute by, so because the cohomology group of abelian varieties were known. We denote alpha 1, the alpha sub 2n are eigenvalues of F bar, the pullback of F bar restricted to the first cohomology group. And then the cardinality of SF bar is written by this, the product of this absolute value. And we have the bound of the spectral radius of F bar pullback restricted to by H1. Sorry, I forgot the paper of this reference, but it is well known. So we can obtain the bound. As a result, we obtain the following bound. So in particular, the main theorem holds for abelian variety case, and the general algebraic group case is reduced to abelian variety case. Any questions? Okay, let's proceed. Finally, we consider general case, but we count the element of SF with codimension 1. Let X be a projective variety, and F is a surjective morphism from X to itself. And we denote by PF by the subset consisting of codimension elements. So this is just prime divisors, which are invariant and having small dynamical degree. And then we prove first the set P sub Fn is finite for any n, and we have the estimate of Pfn, and we denote by Pf to infinity by the union of all P sub Fn, and then Pf infinity is infinite, depend only if there exists an equivariant vibration onto a smooth projective curve such that the restriction of F to C is T1 polarized, and the relative dynamical degree is strictly smaller than the first dynamical degree of F. Here, the relative dynamical degree is defined by this formula. This theorem holds for any projective variety, but in this talk we consider the smooth case for simplicity. X is a smooth projective variety, and F is a surjective morphism with D1 larger than 1. Okay. First, we set rho is the Picard number of x, and m is the integer part of rho over 2 plus 1. And first assume that the cardinality of PF is at least m times rho plus 1. And then we have m subsets S1 to Sm such that each Si has cardinality rho plus 1, and they are pairwise disjoint. And we write Si by this Dij, and Dij J is indexed by J sub I. Here, Si has cardinality rho plus 1, so this exceeds the Picard number. So the Dij are linearly dependent. So we have a decomposition of Ji to Ki cup Li such that the non-negative linear combination indexed by Ki, denoted by Di1, is numerically equivalent to non-negative linear combination indexed by Li, denoted by Di2. We have this numerical equivalence. And here we recall general result. There exists our Cartier divisor LF on X such that the product of LF by F upper star is linearly equivalent to D1 times LF. And LF is not numerically trivial. And for any element D of PF, the intersection of D with LF is weakly numerically equivalent to 0. This means this intersection D dot LF is, and by taking any other divisors, and then it is always 0 for any divisors. This means the weak equivalence. This is because D has small dynamical degree. So if the restriction of LF to D is not numerically trivial, then D should have maximal dynamical degree. So this weak numerically 0 holds. And so this holds for any elements of PF. So in particular, the constructed DIT is also numerically trivial to LF. Here we use a lemma. The following lemma follows from the higher dimensional Hodge index theorem. Let E1 and E2 be effective R divisors on X, such that they are the intersection of with LF is all numerically trivial, and they are numerically equivalent, and they have no common irreducible component. Then first, LF is numerically equivalent to some positive multiple of EI, say CI, and E1 and E2 does not intersect. So apply this lemma to this DI1 and DI2. Then and we can apply this lemma to different DI and DJ. So finally, we can see that DIS and DJT does not intersect for any I, J, and ST. So anyway, the number of DIT is 2m, and they are pairwise disjoint. So we can, and they are not trivial. They are not zero divisors because of this. Because of this, LF is not numerically trivial. So we obtain 2m pairwise disjoint members of PF. And then we use a result of Bogomolov, Piatka, Silberstein. They proved that if there exists primary DI, the indexed by I, and the cardinality is larger than or equal to the Picard number plus 1, and the DI are reduced connected divisors, and which are pairwise disjoint. Then there exists a vibration pi onto a smooth projective curve such that any DI is contained in a fiber of pi, and there are at least 3 members who they forms the whole of the fiber. Using this, we obtain a vibration, and we can induce the self-morphism onto the base. So, and some of DI are coming from pullback of C. So, and LF is numerically equivalent to each D. So, we can see that LF is the pullback of a divisor on C. So, LF is an eigenvector with eigenvalue D1 of F. So the D1 of F restricted to C is also equal to D1F. And so P of F, P sub F is contained in some contained in the fixed fiber or some component of reducible fibers of pi. As a result, we set the number of components of reducible fibers of pi by m. Then we can obtain the bound of PF. PF is bounded by m times rho plus 1, or else bounded by this the number of fixed point of Fc plus n. So the first one is not related to F. So this is not this is preserved. And the second one, it's sufficient to see the growth of the second one. But now Fc is the polarized endomorphism because C is a curve. So we can compute the growth. So we obtain the estimate of PF sub Fn. So finally, we obtain 1, 2, and the third one is already obtained along the proof. So PF is sufficiently large, then we have the vibration. So the third one is also okay. Yes, I stop here. Sorry, I finished very early. Yeah.
Any questions, comments? Oh, there's one. There's one by Xingming. He asking, can SAND imply SDD problem?
Yes, introduction is project proposition. Can I see the question?
You
in the
click
chat.
you can see the chat box.
Yeah. Okay. STD program. Probably not. Probably not. So SND can't show the finiteness of periodic STD subvarieties. And also SAND is only over arithmetic fields. So general cases we can't apply.
Any more questions? So your result in the case of a prime divisor, you have a bound of periodic prime divisor. Can you do the high coordination case? You bound the periodic high coordination subvarieties.
We don't obtain higher coordination result. We can conjecture a similar one. So here PF is bounded by D1 powered by N, but general one is conjectured to bound by N times dimension X. So higher codimensional case, we can conjecture the bound of, say, codimension R case by codimension R elements are bounded by D1 times N times D1 powered by N times R, N times codimension, probably. Yeah, this is a conjecture, but higher codimensional case are not obtained anymore. Except algebraic group case.
So any other question?